So since I'm in the second half of the workshop, I figured I didn't need to do any science introduction. So I'd like to take the opportunity to briefly tell you about where I'm coming from. So just bear with me. So I'm from ASIAA. So we are part of a larger family called the Academia Sinica, based in Taipei. We are a sort of a government-based research institute, including the humanities. Have about 30 institutes. We have about 1,000 research fellows. We don't do any teaching, which could be a selling point depending on your perspective. But we do still have a lot of research students at the institute, and we're centrally funded. But we can also get some additional funds from our Ministry of Science and Technology, who is funding this trip. Astronomy is one of the newer institutes at the academy, but it's also one of the largest. I think it is the largest, actually. We have about 200 people from top to bottom. And as you can see, we cover everything from instrumentation to theoretical cosmology, for example. Just want to point out, we are heavily involved in ALMA, so we're one of the main developers of the Band 1 receiver. So if you're interested in that, you can also talk to me. If you look very carefully on this web page, you will find this tiny link here called job openings that will sometimes lead to big opportunities. But yeah, that was just for just to make it well, get your attention. But so I really only have one main science message I want to convey in this talk, and that is this idea of dust settling, which is sometimes I think taken for granted, right? Particles in the disk settles in midplane, so what? But what I'm going to show you in this talk is that the settling of dust particles could also depend on the solid abundance in the disk. So the more particles you have, the easier it is for dust to settle. In fact, if you have solar metallicities, particle would not settle, and he would find it very difficult to form planetesimals. So take a few steps back. So the story really is motivated by sort of the standard picture of planet formation, right? You build from the bottom up from small grains, micron-sized grains, to protoplanets. And on the two extreme scales, we think we understand what's going on. For very small particles, they can grow by sticking. For very large particles, planetesimals, they grow through gravity. But there's this intermediate regime where you have growth barriers, drift, fragmentation, all that kind of stuff, which makes this scale quite difficult to cross. Now, there are a lot of ideas we've already heard in this talk and in the literature as well, how to overcome this growth barrier. For example, you could trap particles in pre-existing structures in the disk, like vortices, to increase the dust-to-gas ratio. You could invoke special types of gravitational instability. So there's something called the secular gravitational instability that's been discussed in the literature, and that is a type of gravitational instability that's mediated by the dust-gas drift. And of course, we already heard a lot about the streaming instability, which will motivate what I'm going to talk about. So the streaming instability, so this is just a quick simulation of the streaming instability. So this is axisymmetric simulations, but in a cylindrical grid. So I actually initialized the simulation with a linear eigenmode to make sure it actually grows. And as expected, it grows exponentially. It develops, only after a few orbits, it develops very high density dust clumps here. What I do want to highlight here is that this simulation was done with the Pluto code, which does not have a dust module, and I'm not clever enough to implement one. So what we did was something else. We developed this sort of one fluid description of a dusty gas, which is summarized here. So the way we model dust is a little bit convoluted in some sense. What we did was we mapped the dusty gas problem back to hydrodynamics, because there is a connection between a system that is composed of a simple gas like a polytropic gas doped with dust particles, and a system of pure gas with cooling. Now, this analogy works best for small particles, but the analogy is both physical and mathematical, actually. And these are the equations we use, actually, to describe a system of dusty gas, even though it looks like hydrodynamics slightly augmented by unusual source term in the energy equation. But it is a remarkable fact that this set of equations that is almost hydro can give you the most essential results in dusty gas, including the streaming instability. This connection is kind of cool, because what this means is that there's a connection between dusty gas and pure gas, right? So think of a hydrodynamic result in which the energy equation plays a role. For example, gravitational instability and fragmentation. there might be a dusty analog of that, right? And you can think of a dusty result like the streaming instability. Maybe there is a hydrodynamic interpretation of this dusty phenomenon. So then you can ask the question whether or not there is a deeper connection between the two, right? Gravitational instability and fragmentation, and streaming instability and dust clumping. Maybe there's something more there to be uncovered. But anyway, back to the streaming instability. Now, one of the challenges of the streaming instability is that it really only works in a very dust-rich environment. So this is linear calculations, very similar to the one in Vlad's talk, where we calculate linear growth rates of the streaming instability in this case, in viscous disks, but that's not my point here. So my point here is that if you have small particles like Stokes number 10 to the minus 2, 10 to the minus 3, it does make a difference whether or not you're in a dust-rich or dust-poor regime, right? If the disk is dust-poor, then the streaming instability grows quite slowly, so nothing interesting really happens. So if you want to get planetesimal formation to happen, then you really need to be in a regime where the dust-to-gas ratio, the local dust-to-gas ratio, is about order unity or more. So, and that's actually also needed for clumping in the nonlinear regime, right? So the question of planetesimal formation sort of boils down to how do you do that, right? So because when the protoplanetary disk forms initially, it should inherit the dust-to-gas ratio in the interstellar medium, which is about 1%. So you need to increase that by 2 orders of magnitude to order unity dust-to-gas ratio, and then you can talk about streaming instabilities and planet formation. So my question is, how do you actually do this? Of course, there are many mechanisms people talk about in the literature. Dust settling is probably the simplest one, where, okay, you just load the system with dust particles, initially with a uniform dust-to-gas ratio, and then you let the system go, right? And then because of the vertical gravity from the star and also the gas drag, the particles will simply settle to the midplane. This is not an illustration. This is an actual numerical simulation of that process. So starting off with 1%, let the system go. It goes to the midplane with order unity dust-to-gas ratio. So we think, well, then we would conclude that planetesimal formation should happen in this case. But this particular simulation is quite special because I've actually fine-tuned the disk parameters so that the disk is hydrodynamically stable. So the gas is in equilibrium. It doesn't do anything. If you're in that regime, then yeah, particles can just settle, and it's not an issue. So the natural question is whether or not disks are laminar. They are probably not. And we've already heard from the talks so far that there are many hydrodynamic instabilities that could seed hydrodynamic turbulence. So, for example, the zombie vortex instability, convective overstability, and what I'm going to focus on, the vertical shear instability. So this instability really comes from the fact that if you set up a protoplanetary disk carefully, then the midplane rotates around the star at a different rate than the surface layers, for example. And if you have that vertical shear structure, coupled with very fast cooling timescales, which would be typical at a few tens of AU up to 100 AU, and that combination is actually unstable. And result of that instability, this VSI, is hydrodynamic turbulence, and it's largely characterized by very large-scale vertical motion. So the entire disk sloshes up and down, right? So this is a plot of the VSI, plotting the vertical Mach number here. As you can see, yes, the disk goes up and down. The Mach numbers are actually not small, actually few tens of percent. So the natural question is then, what happens to dust particles when you have the VSI, right? Are they going to settle? Okay. So I'll see if I can play it again. But so as you can see, the particles try to settle initially, but then the turbulence kicks in and stirs up the particles. And after a few hundred orbits, the system reaches sort of a quasi-steady state. At the end of the simulation, you end up with what you started with, basically. The dust-to-gas ratio is still perfectly mixed. So in this case, VSI is lethal to streaming instability and planetesimal formation, right? So you can try to overcome that, for example, by having larger particles, right? So if amidst the turbulence, the particles can still grow to certain sizes. In this case, let's say from 100 microns to a millimeter, then because they're bigger particles, they're heavier, they can sort of resist the stirring by the turbulence, and they can then again settle. So small particles remain well mixed, but if they can grow to bigger sizes, then they can again settle. But so far, I'm not saying anything new, right? What I've really described to you is the sort of the classic picture of dust settling, in which you treat dust particles as passive, right? So the particles respond to the gas motions, but not the other way around. Now, in this limit, if you have large particles or weak turbulence, the dust will settle. If you have small particles or strong turbulence, dust will get lofted. But another parameter that comes into the dust and gas dynamics, which doesn't appear in this limit, is the overall amount of dust, right? The solid abundance, which is actually a critical parameter for the streaming instability. So the question we want to know is, how does particle feedback and solid abundance change this picture? And it turns out that the VSI is quite sensitive to the amount of dust in the system when you include feedback. I picked a very extreme example here of a dust to gas ratio of 10% to make my point. Um, but um, but uh, but yeah, but I think it's actually so true at lower dust to gas ratios. Where if you increase dust to gas ratio, what that would do is you're adding particles to the system, so you're actually adding more mass to the system, but you are not adding more pressure, right? So you're not adding more restoring forces. So you are actually making the disk heavier and heavier. So it becomes harder and harder for the VSI to stir things up. You actually actively stabilize the system by dust loading, and that allows the particles to settle. Here are a few more simulations varying the dust to gas ratio from about 1% to zero point 0.1. As you can see, if I stick to the solar or the ISM value of 1%, the particles try to settle. Oh, sorry, this is the dust scale height to gas scale height ratio. The particles try to settle, but the VSI kicks in, stirs up the particles, and it remains pretty well mixed for the rest of the simulation. As you increase the overall solid abundance, it can sort of settle further and further, eventually resists the stirring from the VSI. At about a dust to gas ratio of 5%, it can settle to about 0.1 of a gas scale height. And the number 0.05 is actually kind of special because the gas disk aspect ratio is also 0.05. So that's something to keep in mind there. So the presence, oh yeah, I forgot to mention. Yeah, so this is just a plot of the VSI with dust in the limit of high dust to gas ratio of 0.1. The dust particles have all settled to the midplane. I'm plotting here the vertical velocity. And what happens is as the dust particle settles to the midplane, it actually self-stabilizes. So the coupled system becomes stiffer and stiffer. So you actually get a pretty quiet midplane with VSI turbulent atmospheres above and below the the midplane. So that's a little bit similar to the idea of dead zones, right? This entire thing is meant to be in dead zone. So within the dead zone, there is a deader zone, if you like. Um, so the presence of dust feedback, presence of dust and VSI and feedback sort of complicates the entire picture of dust settling, right? Because you can imagine a situation where some particle settles, it locally it increases the local metallicity, and that will actively stabilize the disk at that location. The stabilization will weaken the turbulence at that location, and that will allow more dust particles to settle, and you might go around this cycle a few times. It doesn't go on forever, because what happens is as the dust particles settle to the midplane, you actually leave behind these turbulent layers above and below, which can continue to perturb the midplane. So that sort of maintains the finite disk thickness. And we can sort of do a sort of back of the envelope estimate of when does dust loading become important for the VSI? Because we can quantify, we can estimate, we sort of know how VSI is stabilized by buoyancy. And we also know how dust loading induces an effective buoyancy in the system. So we can put the two estimates together. And what we find is that if the dust to gas ratio, the sort of the vertically integrated dust to gas ratio, is larger than of order the gas disk aspect ratio, H over R, so 0.05 or something, then the influence of the particle back reaction becomes important for the VSI. And that's a little bit different to what we're used to, this idea that back reaction becomes important when the dust to gas ratio is 1. So in this problem, it becomes important much, much earlier than 1. So one of the consequences of this picture is that we think dust rings should probably be thinner than dust gaps. actually. So hopefully observations in the future, if there are observers looking at the vertical structure as a function of radius, then this might be one way to test this model. So all the results I showed you before were done with the in the sort of one fluid approximation, but recently we picked up Fargo 3D with the full proper treatment of the full two fluid dynamics, dust gas dynamics, and I need to thank the Fargo team, Pablo and Leonardo, for helping me setting up the code. But I picked up the code and I just tried to rerun the problem I just showed you, and yeah, I think it's still true that even in the proper treatment of two fluid, as you increase the dust-to-gas ratio from 1% to about 5%, you can actually enable dust settling against hydrodynamic turbulence due to the VSI. The next question is, well, you have successfully settled the dust, so you would expect planets to form in the midplane. So then you can ask what happens to the dust, well, what happens to the disk when the planet forms, right? So how do planets interact with dusty disks? So this is a topic we heard in a lot of detail yesterday, but I'll briefly recap. So when you put a planet in a disk, it will launch spiral density waves. The inner wake pulls the planet forward. It tries to move the planet out. The outer wake will try to move the planet in. And in the co-rotation region, well, the simplest way to say it is you can get it to do whatever you like, right? So then the question now we want to ask is what happens when you put a planet in a very dusty disk? So this was a summer project led by a summer student, Chen Ziwei. So this is a very dusty disk. So the movie's already started playing, but it's a very dusty disk of dust-to-gas ratio of 0.5. It's very high. I can't really justify it, but anyway, so I have two simulations here. One with a particle size of 0, so in the limit of perfectly coupled gap particles, and the other case with small particles but finite size. And what he's plotted here is he measured the torque acting on the planet from the fluid system in these two cases, and this is the surface density perturbation and the potential vorticity perturbation. And as you can see, when the particles have 0 size, you get results as you expect. There are some oscillations due to co-rotation torques, but then when the co-rotation torques saturate, you are left with the Lindblad torques, and that's a constant value. But when you go to a small but finite particle size, you get these very large-scale oscillations in the torques, which is actually due to potential vorticity generation inside the co-orbital region. And that can actually be traced back to the fact that the system is slightly decoupled. And when the particle and gas system is slightly decoupled, that decoupling can actually act as a vorticity source for the mixture of the system. And since vorticity is actually a sort of a key parameter in the disk-planet problem, the generation of vorticity inside the planet's co-orbital region can produce co-orbital torques on the planet here. And again, this result was done I think last year using the sort of one fluid approximation. But again, we recently checked this with the full treatment of two fluid with the Fargo 3D code. So this is running the same problem, but with Fargo 3D using the proper dust module. And so this was work done by Xie Hefeng at NTHU, where again, yeah, he did verify that the torques undergo these very large-scale oscillations, and there's no convergence. I do want to actually emphasize that Xie Hefeng he's a PhD student at NTHU, but he is not my student. I met him at a conference, and I mentioned this problem to him back in January, and then didn't hear from him since. And then 2 weeks ago, he emailed me saying, "Here are the results." And then I said, "Well, can I please borrow your results to show people?" But he actually also went one step further, because in all these simulations I showed you so far, the planet was held on a fixed orbit, and we just measure the response of the disk to the planet. He went a step further and let the planet go. So the planet, in the red case, is actually migrating or non-migrating. So it does try to migrate inwards, but because of the dust and gas dynamics, the planet actually only oscillates about its radius. And over about 1,000 orbits, the planet only moves in maybe 5% of its initial radius. So the planet more or less stays at the same place for 1,000 orbits. So we need to check this result more, but that's the story so far. So what would happen if a planet was held fixed at an orbital radius for 1,000 orbits? Well, you would form rings and gaps, right? So we are all interested in the origin of these things, of course. So this is a 2D simulation, as was all the case I've presented so far. So the question we wanted to ask next is what happens in 3 dimensions, right? What happens when you include the vertical dimension out of the disk, out of the plane? So I don't have any answers yet, but hopefully I will do because I have 2 incoming summer students that's going to kick off this investigation. And the question we want to ask is whether or not dust settling is compatible with gap opening. And we're interested in this question because when we look at these observed images of protoplanetary disks, we have these very sharp rings, right? That indicates that the dust particles have actually settled. So that's an observational result. But at the same time, we would like these gaps to be due to planets. So, if you have a planet whizzing around the disk, is that compatible with dust settling, right? So we're going to adopt 2 approaches. So I've hired Bi Jiaqing, who is a Robin Dong student in UVic. He's going to try and do full 3D simulations of disk-planet interaction with dust. That's going to be quite challenging, but we're gonna try that. The other approach we're going to take with Tong Siming from Jilin University is that we're going to do what we call axisymmetric disk-planet simulations. Now, this is actually following some work done by Samyang and his student, where we do axisymmetric simulations. We don't put in the actual planet, but we sort of mimic the effect of a planet by prescribing torques on the system. So in an inner disk, we apply a in an inner disk, we apply a negative torque. In the outer disk, we apply a positive torque onto the gas to try to mimic what the effect of a planet should have on a disk. So this cuts out the azimuthal direction, and that gives us high resolution in R and Z. Some preliminary results. So the planet opens up a gap as expected, but unfortunately, the particles don't seem to settle at gap edges. They seem to get puffed up. But these are only test simulations, so there are lots of things to check. I'm 80% sure this is wrong, but I need to understand why it's wrong. In particular, if you look very carefully at this side here, you see these little features here. That could be some indication of some form of instability that is operating because you have a very sharp edge in the dust to gas ratio at these planet gap edges. There is actually a theoretical limit to how sharp of a dust edge you can have in dusty disks, actually, when you account for the vertical dimension. So this is a question that's going to occupy us for the next year or so. Hopefully I will have more results to report to you next time I see you. So there are only 3 take-home messages, I guess. The main one is the fact that the settling process could also depend on solid abundance. That's actually kind of good because that has multiple benefits. Because if you increase the solid abundance, that helps you settle, and that's also needed for the streaming instability to actually give you clumping at the very end. We have a sort of simplified description of dust and gas dynamics that sort of maps the dusty gas problem back to pure hydro, and that might have some applications. And we also looked into disk-planet interaction in the limit of very dusty disks, and in that limit, new effects might appear due to the dust and gas decoupling. So that's almost the end, and I just want to briefly mention some of the ongoing works that I've been involved in to various extents. So if you're interested in any of these topics, or if you have any comments, I would be very happy to talk to you about it. So we have some published work on vortices in protoplanetary disks, for example, including 3 dimensions and self-gravity, or including some non-isothermal effects, some work on observational implications. I have a postdoc currently looking into the streaming instability in 2D disks. There's been some discussion of streaming instability in the context of flat 2-dimensional disks, but I don't really understand what that is. So I've asked him to look into this in a bit more detail, try to clarify what do we actually mean by streaming instability in 2D, right? And as I mentioned, we're doing some analytical work with Sinica on the streaming instability with particle diffusion, looking at stratified disks, VSI turbulence and self-gravity, and dusty vortices and disk-planet interaction. Thank you very much.
Thank you. let's start with, yeah, now behind you.
Really interesting talk. I just, since you've run simulations with both your single fluid model and the two fluid model, I wonder if you could comment on any potential differences here. So particularly like the single fluid model is only valid in for gas motions below a certain frequency and a certain scale that depends on the size of the dust.
Yeah.
It seems possible that you could non-linearly generate motions below this scale or below the time frequency, and that could cause problems. Have you thought about this? Or
Yeah, I think we showed that in the single fluid limit there are spurious instabilities that can appear if you don't filter out the high frequency stuff. So yeah, if we do the single fluid in a 2D simulation, we have to be extra careful about the results. So I think that's probably one issue.
So why is it different in 2D?
Because I think because in 3D you have the streaming instability that comes in, and the growth rates of that is usually much larger. So that probably overwhelms these spurious modes. That's what we found in the initial investigations, actually. Yeah.
Daniel?
Okay, so you said the instrument instability requires raw gas equals raw dust.
Right.
And I hear people saying that a lot. And it's not a little pedantic and point out that although that might be true and maybe it is, but we don't actually know that it's true.
Okay.
The derivation from urine and Goodman was a flat disk, and what I found is that, as you said correctly, that the modes grow slowly, and it's a reasonable argument that that's a problem because then you might diffuse your dust before they collapse. But that's only a reasonable and plausible argument. But no one has actually shown that it's true. I mean, and we can't really, because I mean, no one can run a Turing bot simulation for 10 to the 5 years
Sure.
to see if you just wait a long time, then maybe it'll still work.
Right.
So I mean, yeah, maybe it's a little pedantic, but I just want to point that out.
Yeah. So I guess I meant if you wanted so efficient, really quick.
Well, I mean, 10 to the 5 years is very short compared to
Sure.
the disk lifetime.
Sure. Okay.
But yeah, but we can't test it for that long.
Okay. Thank you.
The result that you are getting putting a planet in a 3D disk. I was wondering what's the size of the particle, the Stokes number that you are using on that simulations, and this is because I see that you may develop strong shock at the midplane because of the two layer of particles going down. And I was wondering what do you think about the validity of the fluid approach on that regime, and even more close to the planet where you have this gap formation and a lot of high velocity dispersion in that region.
Yeah. So we use the Stokes numbers we use are typically 10 to the minus 3. That's our sort of reference value. So in this case, and for the low mass planets we use in those disk planet simulations, the shocks I don't think are very strong. But I think if we were to use like Jovian mass planet or something, then that could become important. I think the single fluid probably doesn't work. Well, I know it doesn't work because Simon told me, right? It doesn't work in that limit.
So I mean, if you have crossing orbit at the midplane, this approach will be wrong.
Right. Yeah,
So
that's true.
So are you planning, for example, to compare with particles?
Not right, not at the moment, but yeah, eventually, if we get our hands on a particle gas code, then that's certainly something we can check with actually. Yeah. So I think that would be important.
Martin, then Jeremy.
Sorry, I was wondering for the cases that you do get the dust to settle in the midplane,
Sure.
do you actually see any signs of the streaming instability for that dust layer?
No, because two reasons. One is the resolution is too poor. Actually, that's the main reason. We have about 50 to 100 cells per H in both directions. That's probably not quite enough to cut it, actually. So it's a resolution issue we can't resolve.
Jeremy? Mike? Is your mic on? Thank you.
Even without the thermally driven instability, it was shown by, well, it's been known for a long time that there's a sort of Richardson or shear instability driven by the dust settling itself.
Yes.
And unfortunately, this is probably not a linear instability, certainly not an axisymmetry. It's subcritical.
Yeah.
Like, so it's important to resolve it. But Shu and Yudin and Shu, in some order, in a paper a long time ago, showed that if the mass loading of the disk is large enough by the dust, it's a similar result, then there isn't enough energy in that vertical shear that's caused by the settling itself to lift all the dust.
Right.
And so some fraction of the dust layer just condenses in the absence of any other source of turbulence into this thin sheet.
Yeah.
So it'd be interesting to see if you can get to the point where you can actually see that happening, even in the case where you set the cooling time to infinity or whatever.
Yeah, so that would be something worth exploring. It's limited in these models because these are axisymmetric simulations. We also checked post-processing. We measured the Richardson numbers and compared to the critical values people measured in the literature, and I think we are not developing KHI.
Well,
yet
it has to be a self-consistent system, because you let the dust settle completely, the Richardson number goes to infinity.
Sure.
It tends to, anyway, complicated.
Thank you.
Sorry, just to comment quickly. There is a linear instability when it's settling as well, and I'll talk about that tomorrow.
True,
but
yes.
It's probably smaller scale than these simulations as well, I think.
Okay, thank you.
Sorry, that was kind of just an advert.
Okay. Thanks again.
Thank you.